G'day viewers. In this segment we're going to talk about switches, which are a very widely used technology to connect computers together into small networks inside buildings. Okay, so we've talked about multiple access schemes a lot. Now they are very widely used for wireless networks. 802.11 was the popular example. But when we're using wires, rather than have the host run a multiple access control protocol, the method which is used today, which is vastly more popular, is to connect all of the hosts to a switch device in the middle. You can see in this figure at the bottom here, I have 4 different boxes which are all wired to one switch. The switch will provide connectivity between all of these different devices. This architecture is the basis of switched Ethernet or modern Ethernet, and it's used ubiquitously to tie together computer equipment in all manner of buildings. Let's just drill down in a little more detail. So the scenario is like this. Inside your building, your home, your office, the campus, you have different hosts, and these hosts are connected via a twisted wire cable, a twisted pair cable typically, to a box called a switch. This switch has many ports, so you can connect many different hosts to it. Somehow this switch is going to provide connectivity between all of the hosts so that when they send frames, because we're still operating in the link layer, when they send frames, the frames will go from one host to the right other host. Typically the wiring is done so that the switch will be in some kind of central location and all of the wires in your building will be run to a wiring closet in a convenient location. So the big question for us is what's going on inside this box to provide all of the connectivity? That's a pretty interesting question. If you remember back to our diagrams on protocol layers, I said something like this, that all of these different kinds of boxes, there are many boxes that have cables attached to them. They're distinguished by the functionality of what goes inside. And we can draw different kinds of protocol diagrams to describe the processing that goes inside. In a hub box or a repeater box, the devices operate at the physical layer. So they're really just connecting bits around, moving bits around. In a switch device that we're looking at now, the functionality inside the box runs at a link layer. So it's connecting frames from one port to another port. And in a device called a router, the functionality inside the box works at the network layer. So it looks at the details of IP packets, in the case of the internet, to work out which way to send them. We'll get to routers later on, so we're not going to look at IP packets and routers now. Instead, we're just looking at switches, operating at the link layer, sending around Ethernet frames. Well, to understand that, we'll go over both hubs and switches, because this will show us the difference between the two. We'll start with hubs. These are a physical layer device. In a hub, here's a inside view for what could be going on inside this box. We have all of the different lines coming in. These lines come from some host. They attach to the ports. Inside the box, if this is a hub, as a physical layer device, you could simply imagine that all of the ports are wired together. This will provide physical layer connectivity, and that's all we need. So for instance, if a frame comes in on this port from some host and it's all wired together, that same frame will go out on all of the other lines. Functionally, this is equivalent to the setting on the right, where if one host sends onto the wire, the frame will be delivered to all of the other hosts. It's just another way of wiring it. It's generally more convenient than winding one long wire through all of the different offices, because now we can run twisted pair to a central wiring closet. It's also more reliable, because if we lose one particular wire here, well, some host is out of luck, but chances are that the rest of the hosts are still able to communicate. However, if we break this wire here, you generally do more damage. You might have broken your LAN in half. It just doesn't work anymore. The signals get messed up too. Inside a switch, something very different is going on, even though it looks like the same box. Switches operate at the link layer. So as the frame comes in now, the switch will look at the link layer information, that's the source and destination Ethernet addresses, to be able to forward this frame out the right output port. This means, for instance, that if, let's just say I just number these hosts, 1, 2, 3, 4. if I send a frame in here, it might be destined to the host on port 4. I would then send it through the switch fabric and out port 4. At the same time, the host on port 2 might be sending a frame to the host on port 3 using a different path through the switch fabric. The switch fabric here is shown as a grid. You could just imagine this as almost a street map and traffic lights. Depending on the addresses that are on the frame, different kinds of traffic lights or switches here have been turned on or off to connect different input ports to different output ports. And so that is how we can use different parts of this switch fabric to connect different input hosts to different output hosts at the same time. Here's just a cleanup of that figure where 1 is sending to 4 and 2 is sending to 3 at the same time. I'll note a couple of other things. First of all, I just sort of draw a line between a host and the port here to represent a link. Typically, for all switches you get today, this is a full duplex link. So even though I draw one line, really you might think of this as having two halves. Inside the cable there's usually a wire going one way and a wire going another way to make it full duplex. And this port really has an input and an output port structure. Yes, so they're full duplex. Also, what that means is that I can use, because I can do this sending in parallel, there's no multiple access control protocol for a switch. The host just send the frame into the switch when they're ready, and the switch will deal with making all of the right connections to send information at the same time. This is quite different than a hub, for instance. With a hub, when one host sent, the message was received on the wire at all of the other hosts. This means that two hosts couldn't send at the same time. Those hosts need to use a multiple access control protocol to coordinate their actions. With a switch, there is no MAC protocol. The lines are full duplex, they send into the switch works it out. This new method of working, however, does pose some problems. There is a lot going on inside a switch. In particular, you might wonder what happens if two different inputs are sent to the same output. So let's say that the first host here is sending a packet through the fabric to the same host on the output side. Well, what happens if all of the other hosts are also sending there? It's just a very popular destination. So we're all sending through the switch fabric to this one output. This can't happen at the same time if the lines are the same speed. Only one frame could be going in or out of a given port, maybe in and out if we can use it bidirectionally at the same time. The other frames which are coming in from other ports, which are destined for this one port over here, will need to be stored somewhere temporarily. For this reason, a switch has buffering, either on the input side of the switch or the output side, or both. You can see I've shown the buffering here as the pink here. So this is a little bit of storage memory to temporarily store frames until they can be sent on an output port, the right output port. The issue here, however, is that this buffering is fine if there are very short-term mismatches. Two hosts sent to one given output, and well, it took 2 frame times to send it out, so a frame had to be buffered for 1 frame time. But it's not going to work. Even buffering won't solve the problem if these hosts are sending to if multiple hosts are sending to one output in a sustained manner. If that's the case, the frames will build up inside the buffers. Eventually the buffers will be full and we will have loss. Now this is an example of some kind of contention or congestion happening inside the network. Because of this loss, as you send packets or frames across a network, they can almost disappear inside the network. They can be thrown away because the network could not support the traffic patterns. We're going to look at this issue much more later on when we get to TCP/IP, because this same sort of issue happens as you send packets across the network. They can be lost due to a lack of buffering inside switches. For now, we're not going to worry about it too much, and we're going to say if the switch is well engineered, this can happen, but we'll hope it won't happen very often. So switches and also hubs have some significant advantages over just connecting all of the hosts to a single shared wire, as was the case with classic Ethernet. Hubs and then switches became possible really due to Moore's law as electronics sped up greatly and also became a lot cheaper. And nowadays they're prevalent. They're what you find everywhere. They're not just possible because of technology, but they have definite advantages. It's more convenient generally to run wires to one central location rather than to sneak it through the offices. Imagine what you have to do to change it if you want to add another host and you've just got this one wire. They're also more reliable, as we said before, in that if the wire fails, you might lose a host, but you probably have connectivity for all of the other hosts in the network. This is different than a classic Ethernet. If there's a break in the Ethernet, actually it doesn't work for all hosts for electrical reasons. You may wonder if the switch itself is a problem for reliability. It is, after all, a single point of failure. You blow up the switch, you lose connectivity to all hosts. That's true, but if you lose connectivity to all hosts, you know exactly what to do. Go find the switch, take it out and put another one there. So it can be repaired fairly easily. It's not hard to find where the problem is. The other key advantage for switches is this. Switches offer scalable performance. This is a real win. With our single shared cable, maybe you have a 100 megabit per second cable, you attach 10 hosts to it. Each host, its fair share is maybe 10 megabits per second of bandwidth. With a switch, because we can send frames in parallel, you might provide 100 megabits of bandwidth per port. So every host then is able to send and receive it up to 100 megabits per second. Performance is much more scalable for these switches. Okay, so I'd like to go into one particular issue for making switches work. You might have wondered as I talked through there how switches, if they deal with Ethernet frames, find the right output port to which to send a frame. This would be easy if frames carried port addresses, send me out output port number 7, but they don't. The addresses which are on these frames are Ethernet addresses. They indicate a host, either the source host or the destination host. Now, that destination host might be plugged into any port on the Ethernet switch. We could imagine having someone manually configure a big table. This would be a terrible job to have. We don't want, that's exactly what we want computers to do. So let's try and solve it with an algorithm. And we also want an algorithm which will allow hosts to move around. You might move your computer to another office and connect it to a different switch, and that should be okay too. So we need to find some way when frames come in and we just have a source and destination address to work out what output port to send that frame to. The algorithm we use to solve this problem with switches is called backwards learning. It works as follows. So the switch needs to build up its own table that maps between addresses and ports, so it knows which port to use. It does so as follows. Step 1, first thing we do is we build up this table. An insight to allow us to fill in this table without having any human configure it is to note that Ethernet frames carry both source and destination addresses. So if you see a frame on a port, you can look at the source address and say, oh, I see a certain source address, so this port is where this address lives. If I ever see a frame which is destined to this same address, now I know what port to send it on. So you look at the source address of the frames to find out what port they're on. That's the backward bit in backward learning. Usually you might think you just look at the destination to work out where to send the frame, but by looking at the source, we can also work out where people live. The second step is what you do to forward these frames. You just got a frame on an input port destined for a particular destination. What do? You look up your table. If you know the port where it lives, because you've learned it earlier somehow, then you just send it to that port and you're done. What if you don't know? What do? In that case, you broadcast it by sending it out all ports. You just say, I don't know, it's attached to some port, I'll send the message out all ports. That way it's going to get to the right port destination. It'll also get to a lot of other ports and they'll just have to ignore it. Let's see how that works in action. So the very first time the network's used after it's powered up, A is going to send to D. No one knows anything at this stage. So A's frame comes in, it just says, hey, I'm a frame from A, I'm trying to reach D is the destination address. This switch It's clueless, it's just been turned on. It says, I don't know, there's nothing in my table. So therefore, I'm going to forward this frame, I'm going to broadcast this frame, I'm going to send it out all ports. Well, phew, it reached D, that's very good. It also reached B and C. Oh well, not a very efficient use of bandwidth. We also learned something here. We learned that A is on port 1. Right? That's a valuable bit of information. Okay, so this is what happened. Now, step 2. Let's assume, because most communication involves requests and then replies, sometime later D is going to send a frame back to A. What will happen? Here's D, it sends its frame in destined for A. At this stage, the switch can look up its table here and say, yep, I'm just going to send it directly out that port. Wonderful. We did not have to broadcast it out the other ports. Here we are, cleaned it up, I just changed the color so you can see them. Oh, I should have said we also learned something. We also learned that D is on port 4 by looking at the source address as the frame came in. This is the normal situation now. Everyone sent a little bit of traffic and we've learned, because if they're using the network they're going to send some traffic, hosts, then we learn what port they're on. Now we're fine. Let's imagine now that A happens to send another frame to D. The frame will go into the switch. It'll come in port 1. The switch will know, yep, D, port 4. It will just send it there. Now we're sending frames between the port 1 and port 4, between A and D, fine, without broadcasting and sending extra traffic to other hosts. That just happens once, and this mechanism is fully automatic. We've learned how to get from one port to another with no configuration from a human and in a way which is fairly efficient. So that's pretty cool. There's something actually that's even cooler about this. This same mechanism works if you run it independently in the different switch. They're shown here as B1 and B2. Even if you have some hubs in there here too, by the way, there's a hub in here, H1. Assuming there are no loops in the topology, this is a crucial assumption. We're going to want loops in the topology, or at least we're going to want to allow them. So in the next segment, we'll handle the case where there are loops in the topology. For now, we'll assume there are no loops. Then the mechanism I've shown you will solve the problem. Let's see what would happen when A sends to D and then later D is going to send to A. Okay, A sends to D, here the frame comes in. With beginning of the world, everyone's just woken up. This switch, B1, has no clue. This switch says, okay, I will broadcast it out all of my ports, because I don't know. I'll also remember that if I ever want to get to A, I use this port, port 1. Okay, so this frame is going to go to host B and C. It will also go over this link and enter switch B2 through this input port. B2 actually doesn't know that it's come from another switch. As far as B2 is concerned, A could be directly connected here. It really doesn't know. It can't see the overall topology. But B2 runs exactly the same algorithm. It gets something in from A, destined to D. It's clueless also. It learns, hey, A is here. D, no idea. Well, we'll just send it out all of the ports. That's what we do. We broadcast if we don't know. It'll go to G. It'll go to D. Yes, that's what we wanted. It'll also go out here to the hub. The hub, by definition, wires everything together, so it will go out the other ports. It'll reach E and F. Wow. So A's frame went everywhere. But at least it got to D. Here's that again, and now let's look at what happens next. Now D is going to send to A. Here's D's frame, comes in on port 1 on this switch. It wants to get to A. Well, switch B2 actually remembered that the way you get to A is you send out this port. So it'll simply send it out that port. There's no need to broadcast. It'll come in this port. Switch B1, as far as switch B1 is concerned, this could have come in directly from D. D could be plugged here, it doesn't know. Switch B1 looks at the destination, that's A, it looks at its table and says, yep, that just goes out port 1 here, no worries, done. No broadcast, we now have an efficient way for D to send to A. And of course, you know where I'm going here. You can work through yourself the case of how A sends back to D, and you'll see that we're using the switch very efficiently. So this algorithm extends naturally to topologies with multiple switches and hubs. That's pretty cool. Now you know a lot about how switches work. This is how a modern switched Ethernet works. We've just not handled one condition, and that's that there might be loops in the topology. I'll get to that in the next segment.